Hello, today we're going to learn how to solve systems of differential equations using the eigenvalue problem. So remember when we had one linear constant coefficient homogeneous differential equation, we expected that we'd get a solution of the form y is equal to e to the mx. So we should still expect that we're going to get something similar to that when we have a system of linear constant coefficient homogeneous differential equations, x prime equals ax. In fact, we can assume that the solutions to our system will be of the form x of t equals some vector k1 through kn, or the components, times e to the lambda t. And so if we were to write this out, I'm going to use the example where we have a system of equations with a dx dt, dy dt, and a dz dt. Then what this is saying is that we have a vector x, y, z that is equal to some other vector that has constants, some k1, k2, k3, times some e to the lambda 1 t. Okay, and so the lambda 1 is kind of serving the place of the m from before, where the m was the root of the auxiliary equation. Now the lambda is the root of the characteristic equation. And the k1, k2, that is the eigenvector that is associated with the lambda 1. So we can even label these. This k vector, that's going to be the eigenvector, I'll call it e vector. And the lambda 1, that is the eigenvalue, and I'll label that e value. Okay? So we can write this more compactly, and then what we're going to do is we're going to write it as x equals k e to the lambda t. That's our more compact form. And then we can easily calculate x prime based on the fact that t is the variable that we would be differentiating with respect to. K is a constant vector. Lambda is a constant, and so x prime would just be k lambda e to the lambda t. And then we could substitute that into our matrix equation and work from there to try to derive our eigenvalue problem. Like, how are we going to find our lambdas? How are we going to find our k's? Okay, so when we substitute these forms for x and x prime into our matrix equation, x prime equals ax, we're going to get this equation. K lambda e to the lambda t is equal to ak e to the lambda t. Okay, so on the left, we have the x prime, and on the right, we have the ax. Okay? Now, if we rewrite this as an equation to solve, just as we did before when we were doing the matrix review, and we recall that we can always rewrite any vector k as I times k, where I is the identity matrix, then what happens is the following. So first, we move the k lambda e to the lambda t to the same side of the equation as the ak e to the lambda t, keeping the a side positive. And we set that equal to 0. And then notice that we could factor out an e to the lambda t from each of the terms because that's constant. So then we have in parentheses ak minus lambda ik. So now the k has been rewritten as ik. All of that times e to the lambda t will equal 0. Well, the thing with e to the lambda t is that it's not going to equal 0, right? That's never equal to 0 for any lambda value or t value. But then we notice further that the k can be factored out on the right, not the left, but on the right. And so we get this final form of a minus lambda I, that's going to be our coefficient matrix, times k, this vector that we're trying to find, times e to the lambda t is equal to 0. Okay? And so this boils down to really the more simplified form of a minus lambda I times k is equal to 0, because we know e to the lambda t cannot be 0 for all t that are in the real numbers. Now, this whole principle is going back to what we covered when we were just solving the general eigenvalue problem, but the idea is that we're not very interested in k, the eigenvector, being 0. That would be a trivial solution. So we are not interested in k equals the 0 vector. That would be the trivial solution. And so we're really going after how can we get non-trivial solutions to this matrix equation. So we're going to do the same thing as before. In order to guarantee that we have a non-trivial solution, we need the determinant of a minus lambda I to be equal to 0. And so when we say that the determinant of a minus lambda I is equal to 0, what that's going to do is it's going to give us the lambda values that would make it so that a minus lambda I, when we try to solve for k in that equation, we end up with a row of zeros. And so we're going to get one of the values, k1, k2, or k3, could be anything. And then the other two values would be in terms of it. So very similar to what we did in the previous appendix. So solving this determinant equation, that's going to allow us to find the eigenvalues, lambda I. And once we can find the lambdas, then we can find their corresponding eigenvectors, k sub I. And the solutions to the system will be composed of the eigenvalues and eigenvectors. What that means is that each solution, x sub I, will be equal to its corresponding eigenvector, k sub I, times e to the lambda I, I'm missing my I there, t. Let me write that a little bit better. This should be x sub I is equal to k sub I times e to the lambda sub I t. Okay. Now finding the eigenvectors that are associated with each eigenvalue will be a slightly different process depending on whether we have eigenvalues that are distinct in real, repeating in real, or complex. And so we're going to go through the process. We're going to learn how to find the eigenvectors by walking through some examples. And we have our process here that we're going to follow. And we're going to work through the different cases where we have distinct real, repeated real, and complex solutions for the eigenvalues. Okay? So here's our process. We're going to solve the system a minus lambda ik equals 0. Or in other words, in parentheses, a minus lambda I equals 0. In the process of solving, we have to come up with a row of zeros, or possibly more than one row of zeros, in the case of having repeated eigenvalues. And this will allow us to get a non-zero eigenvector. If we don't, then our solution would be a 0 vector, and that's not what we're after. Those would be trivial solutions. So if you're getting a 0 eigenvector, that means you did something wrong. It's an indicator, okay? Once you have the eigenvector, the solution associated with that eigenvalue is x sub I equals k sub I e to the lambda sub I t. And we continue this process for every eigenvalue. And at the end, we form the general solution by saying it's the linear combination of all of the solutions that we found. Okay? So here's the first case, distinct real eigenvalues. An n by n system of differential equations will have n unique solution vectors. And so x1 would be, k1 e to the lambda 1t, x2 would be k2 e to the lambda 2t, and so on and so forth. And then the general solution would be comprised of c1x1 plus c2x2. I have a lot of typos in here. Sorry about that. Plus all the others. Okay? So we're going to start with a 2 by 2 system. dx dt equals minus 6x plus 2y, and dy dt is equal to minus 3x plus y. First, I want to rewrite this as a matrix equation. That's always my first step so that I can identify my coefficient matrix. So this is x prime on the left, that takes care of dx dt and dy dt, is equal to the coefficient matrix. So the coefficients for the x's in the first column are -6 and -3. The coefficients for the y's in the second column are 2 and 1. And then this is times some x vector that has x and y in it. Okay, so this is our A, the -6 to -3, 1. So then we need to calculate the determinant of A minus lambda I. That is, we look at the straight up and down bars. We're going to put across the diagonal, we have the A components, whatever they are, then minus lambda. So we get minus 6 minus lambda, and then 2, and then negative 3, and then 1 minus lambda. So we calculate this determinant by using that diagonal product that we learned, and that's going to give us, in quantity, minus 6 minus lambda, times in quantity minus 1 minus lambda, minus the negative 6, so that'll be plus 6. And this is all supposed to equal 0. Now, before I can solve this, I have to FOIL and then combine my like terms, make it all pretty, and factor it. So when I multiply everything out, this becomes, I get a lambda squared, I get a plus 6 lambda and a minus lambda, so that's a plus 5 lambda. I get a minus 6, and then I get a plus 6. So those are going to go away. Okay. All right, so then I just have lambda squared plus 5 lambda is equal to 0, and that means we can factor out lambda. That leaves behind lambda plus 5. That's equal to 0. So we get lambda equals 0, and lambda is equal to negative 5. Now, I have made many statements about k not being equal to 0, but I said nothing about lambda being equal to 0. That's perfectly acceptable. All right, so let's go ahead and deal with, we're going to call lambda 1 will be the 0, and lambda 2 will be the negative 5. So for lambda 1 equals 0, we're going to solve in parentheses the a minus 0I set equal to 0 for k1. So we want to find our eigenvector given that we know the eigenvalue associated with it. So we plug in lambda equals 0 into the a minus lambda I matrix. That's going to give us minus 6, 2, minus 3, 1. Put in an equal bar and put your zeros on the right-hand side. Now it looks like we could divide the first row by a negative 2. So in other words, I multiply by negative 1/2 the first row. And what happens is it becomes a 3, a negative 1, a 0. The second row is still negative 3, 1, 0. And by doing that, now I can see that if I add row 1 plus row 2 to get a new row 2, I'm going to clear out that second row. So the first row is 3, negative 1, 0. Second row becomes 0, 0, 0 when I combine the two rows. So row 2, that is telling me that K2 is what we call free, okay? It can be whatever we want. And so usually what we say is we're going to let K2 equal C, okay? But we can also choose K2 to just be convenient, and I'll show you what I mean by that after we work with row 1. Row 1 is saying 3K1 is equal to K2, which means K1 is equal to 1/3 K2. Okay, so now what I'm going to do is I'm going to say let's let K2 equal 3, because that's a convenient value so that I'm not going to deal with fractions. Then K1 is equal to 1/3 times 3, which is equal to 1. So our K1 eigenvector is equal to a vector that has components K1 and K2. And K1 is 1 and K2 is 3. Okay. The solution associated with lambda 1, I should just write it out, lambda 1 is 0 and K1 is 1/3 is x1, and it is going to equal the K1 1/3 times e to the lambda t, which that's going to be e to the 0t, or in other words, x1 is just equal to the vector 1/3. Now, another thing I should state about right now is that the eigenvectors will always point in the same direction. However, they are not unique because I was able to choose any value I wanted for K2. I could have let K2 be equal to 1, and then K1 would have been 1/3, which is, it would just end up being a multiple of the actual eigenvector that I got, okay? So just so that you're aware, the homework online is prepared to handle that, okay? All right, so we've got one of the eigenvalues and its associated eigenvector out of the way and the solution that it forms. Now, let's deal with lambda 2 is equal to -5. Okay, so for lambda 2 is equal to -5, we're going to solve. A minus a -5 will be plus 5i, set equal to 0 for K2. Okay. Now, when I plug in a -5 to the a minus lambda I that I can see up here, what I'm going to get is a -6 plus 5, and then I have my 2, I have my -3, and I have a 1 minus a -5, so it's 1 plus 5, and then my equal bar and zeros on the other side. This becomes, after I simplify things, -1, 2, 0, and a -3, 6, 0. If I was to take row 1 and multiply it by a -3, then that first component, the -1 times a -3, it would become a +3 and it would clear below. So let's try that. -3 row 1 plus row 2 will equal the new row 2. And I'll write out what that looks like. So the row 1 would now be 3, and it would be a -6 and 0. Row 2 would be the -3, 6, 0. When we add them together, we get a row of zeros. So now we have the matrix with elements -1, 2, 0, and then a row of zeros. Okay? All right, so row 2 is saying that K2 is free. Again, row 1 is saying -K1 is equal to -2K2. Or in other words, K1 is equal to 2K2. So I'm going to say let's let K2 equal 1, since it could be anything that we want. Then K1 is equal to 2 times 1, which is 2. So our eigenvector, our K2 eigenvector, will have components K1 and K2. K1 is 2, K2 is 1, and that's our eigenvector. Okay, so the solution associated with lambda 2 equals -5 and K2 equals 2, 1, the eigenvector, is x2, which it will be K2, that's our 2, 1 vector, e to the lambda, so that's -5 times t. Okay, so we have our two solutions. We can now form the general solution to the system is x with a hat on it is equal to c1 x1 vector plus c2 x2 vector. And so what that looks like is x is equal to, the first solution we got, x1, is just 1, 3. So we have c1 times the vector 1, 3 plus c2 times x2. I'm going to put the e to the -5t out in front, and then times the vector 2, 1. And that's it. That's our solution. Okay, another way to see it, just so that you're aware, is, let's just say another way to view this, because sometimes this makes it more clear for people. That x factor vector has components x of t and y of t, and it's equal to, now if we were to combine all the parts of the c1x1 plus c2x2, the first row becomes c1 plus 2c2 e to the negative 5t. The second row becomes 3c1 plus c2 e to the negative 5t. And then each of the rows looks a little bit more familiar. Each of the rows looks kind of like the solutions looked when we were dealing with one differential equation, linear constant coefficient homogeneous differential equation. Okay? And I would say that either way is acceptable for entering your answers, both in the online homework platform as well as on quizzes and exams. Okay? All right, let's look at the next case where we have repeated eigenvalues. There are two cases that are going to come up. Sometimes, even though an eigenvalue repeats, we still get two eigenvectors for it. And the way that shows up is we get two rows of zeros, or two free variables in the system when we solve a minus lambda I set equal to 0. And those eigenvectors will be linearly independent. And that's like the case that we hope for. We want it to be such that if we get lambda 1 repeats itself twice, we get two rows of zeros for two free variables, and that helps us get our two linearly independent eigenvectors. However, that does not always happen. Sometimes when we have a repeated eigenvalue, we only get one row of zeros, and so we only have one eigenvector associated with it, and then we're kind of short in our solution, okay? And so what we'll have to do is this process where we're going to solve for p in x2 is equal to kt e to the lambda 1t plus p e to the lambda 1t. And that's going to allow us to get our second linearly independent solution, okay? x2 will be a linear combination of our k vector that's from x1, or sorry, from that one row of zeros, along with this p vector that we have to find. The k is the one that we've already found. So to find p, what we're going to do is solve a minus lambda 1I all times p set equal to the k that we already know. And then we're going to find out what p is. And then the general solution would be x is equal to c1 times k e to the lambda 1t. So that's the x1 vector, plus c2 times kt e to the lambda 1t. That shows like how that's the repetition. That's kind of like what we saw when we were dealing with these with just one linear constant coefficient homogeneous differential equation, but then plus the p e to the lambda 1t. So this is all the x2 vector. All right, let's see a couple of examples. I'm going to do this one right here where we get enough rows, we get enough free variables, and then we'll do another one where we have to find the p vector. That way you're prepared for each of the possibilities, okay? So in this example, we're asked to solve this particular system. It's already written in the matrix form, okay? And so this matrix of coefficients, that's our A matrix. So we need to find the determinant of A minus lambda I first. All right. What we do is we take our 3 by 3 matrix, and along the diagonal, we're going to put in the minus lambdas. So we have 3 minus lambda, 2, 4, 2, 0 minus lambda, 2, 4, 2, 3 minus lambda. Okay, we're going to take a determinant there, and I'm going to focus on the first row, first column. Remember, that's where we have plus. In the second column, we have minus. In the third column, we have plus. Okay. So this is equal to a 3 minus lambda in quantity times the 2 by 2 matrix that gets left behind when you delete the row and column that 3 minus lambda is in. So that has a minus lambda, a 2, and a 3 minus lambda. minus 2. So I'm moving on to the second column now. And I imagine the row and column that it's in deleted. And I come up with my 2 by 2 determinant, which has 2, 2, 4, and 3 minus lambda in it. Then we move on to the next column with a 4. So I get plus 4 times the 2 by 2 that remains when we delete the column and row that 4 is in. So it's 2 minus lambda, 4, and 2. Okay, now I'm going to go ahead and do all of my diagonal products that I need for my 2 by 2 determinants. And here's what we get. We have 3 minus lambda in quantity, brackets, negative lambda times 3 minus lambda minus 4. Close the brackets. Okay, that takes care of the first one. Minus 2 times brackets, 2 times 3 minus lambda minus 8. Close the brackets. Plus 4 brackets, and here we get 4 minus a negative, so it'll be plus 4 lambda. Okay, next, I need to figure out if any of this is going to work out nicely to factor, okay? So my advice to you is to first simplify what's in each of the brackets, okay? And then notice if anything can factor out of all 3 terms, okay? We only have 3 terms here. We just have a lot of algebra to do in each of the terms. So I'll do that first. And then this should all be equal to 0. So I keep my 3 minus lambda factored out. Inside my brackets, I get a lambda squared minus 3 lambda minus 4. Then I have my minus 2. Inside the brackets, I have a minus 2 lambda plus 6 minus 8 gives me a minus 2. Okay. Then I have a plus 4 times, I'm going to rewrite that as 4 lambda plus 4. All of this is equal to 0. Okay. Now, in the first set of brackets, that factors. So I have my 3 minus lambda still. In my brackets, I now can write parentheses. This factors as lambda minus 3 times lambda plus 1. No, it does not. That's lambda minus 4. Okay. All right, in the next one, okay, so I'm looking at what I have here for my factors. I have 3 minus lambda, lambda minus 4, and lambda plus 1. And the next 2 terms, I want to see if by factoring out a constant, I might leave behind a lambda plus 1. Okay, so in the second set of brackets, I'm going to factor out a negative 2. So it'll combine with the negative 2 outside to become plus 4 times lambda plus 1. And then the next set of brackets has a 4 in common, so I factor it out to get plus 16 times lambda plus 1. And this is all equal to 0. Now notice we still have 3 terms, and each of the terms has a lambda plus 1. I do notice that the second 2 terms can actually just add to give me 20 of these lambda plus 1s. Okay, I'm going to factor out a lambda plus 1. And then leave behind in brackets a 3 minus lambda, a lambda minus 4, and a plus 20. That's all equal to 0. So I walked through this so carefully because I know that this is a sticking point for many, many people. Number one, if you were to FOIL all of this out, you might make a mistake. You may or may not, right? And if there's a mistake, this all falls apart, okay? Number two, you might multiply it out correctly and then be stuck, not realizing that you can just look up a root in your graphing calculator, factor out the root using long division or synthetic division, and then factor the rest of it. By being strategic in how I multiply things out, typically I can find a common factor in the terms and get that out and leave a quadratic behind, which I can handle. Okay, moving on. So I have my lambda plus 1. Inside my brackets, I have a negative lambda squared, and then I get a 3 lambda and a 4 lambda for a 7 lambda. I have a minus 12 and a plus 20. That's equal to 0. Okay, so now I have my lambda plus 1. Inside I have negative lambda squared plus 7 lambda, and then a plus 8 is equal to 0. I'm going to factor out a negative 1. So it'll be a negative on the outside. I have my lambda plus 1, and then I have lambda squared minus 7 lambda minus 8 is 0. And now that does factor. This will give me negative times lambda plus 1, lambda minus 8 times lambda plus 1 is equal to 0. So it looks like lambda 1 is equal to, I'm going to go with the 8, and lambda 2 is equal to a negative 1 twice. So we have our repeating eigenvalue. Okay? Now notice that this was a lot of work just to solve the determinant. And because there's a lambda in there, you don't get to use your calculator. It won't help you. So you've got to know how to do this by hand. Okay? Practice will help a lot. Let's go ahead and deal with lambda 1 is equal to 8. So for lambda 1 is equal to 8, we will solve a minus 8I set equal to 0 for k1. Okay, a minus lambda 8, a minus 8I. I'm going to plug in the 8 to my a minus lambda I, and I get 3 minus 8, a 2, a 4, and a 0. I get 2, and then I get a minus 8, 2, 0. And I get 4, 2, and 3 minus 8, 0. Then I simplify things, and this becomes a negative 5, 2, 4, 0, a 2, negative 8, 2, 0, and a 4, 2, negative 5, 0. None of these are very nice numbers to work with, but we can still do it, okay? The first thing I'm going to do is I'm going to take row 2 and divide it by 2, or in other words, multiply it by a 1/2. Row 1 is still negative 5, 2, 4, 0. Row 2 is now 1, negative 4, 1, 0. And then we have 4, 2, negative 5, 0. Okay. If I take row 1 and then I add it to 5 times row 2, that's going to give me a new row 2 that I can work with. Okay, it'll clear that 1 that's in the bottom. So this will equal the new row 2. So I'll write out what this means. Row 1 is negative 5, 2, 4, 0. Row 2, when it's multiplied by 5, gives me 5, negative 20, 5, 0. Adding the columns, I get 0, negative 18, 20, and 0. Okay? Now, that's my new row 2. So I rewrite my matrix. Row 1 is still negative 5, 2, 4, 0. Row 2 is now 0, negative 18, 20, and 0. And row 3 is 4, 2, negative 5, 0. Okay. Now, I need to use row 1 to clear row 3. And the only way I could do that is if I was to multiply row 1 by a 4. So 4 row 1 plus 5 row 3. And that would give me a new row 3. So the math on that, let's kind of put this in a different color. 4 row 1 would give me negative 20. It'll have an 8. I'll have a 16 and a 0. And then row 3 by 5 will give me 20, 10, negative 25, and 0. When I add columns, I get 0, 18, and then that looks like a negative 9 and 0. Yeah, okay. And so now my matrix becomes row 1 stays the same, negative 5, 2, 4, 0. Row 2, I kind of want to fix row 2, but I'm not going to. I'm going to leave it as it is because it will work. 0, negative 18, 20, 0. Row 3 is now 0, 18, negative 9, and 0. Hang on a second, I did something wrong. Right here. 4 plus 5 is not 20. Very much not 20. This should be a 9. Okay, I'm going to go through and just fix that so that it is a 9. And right here. Fortunately, I haven't used it to do anything, but the reason I got suspicious was that I was going to use row 2 to clear row 3, but I wasn't going to get a row of zeros, and that would have been bad. Okay. All right, so now if I add row 2 and row 3, that's going to give me in my new row 3. And so row 1 stays negative 5, 2, 4, 0. Row 2 stays 0, negative 18, 9, 0. Row 3 is now a row of zeros because negative 18 plus 18 is 0 and 9 minus 9 is 0. Okay. The last thing that I want to do is I want to take, let's see, we can do this a number of ways. I'm going to take 1/9 of row 2. Yeah. So 1/9 row 2. So I have a negative 5, 2, 4, 0. 1/9 row 2 gives me 0, negative 2, 1, 0. And I have my row of zeros. What I'm doing right now is I'm going to clear above. We haven't done this before. I'm going for more of a reduced row echelon form to make my life easier when I solve for my K1s, K2s, and K3s. Because I can see that I could clear this 2 that's in row 1 by using the negative 2 in row 2. And so I would just take row 2 plus row 1, and that would give me the new row 1. Let's see what that looks like. Row 2 is going to be 0, negative 2, 1, 0. Row 1 is negative 5, 2, 4, 0. When I add columns, I get negative 5, 0, 5, 0. Okay, and then let's just check my work there. I want to make sure I didn't do anything wrong. Okay, I think that's good. All right, so my new row 1 is negative 5, 0, 5, 0. My row 2 is 0, negative 2, 1, 0. And then I have a row of zeros. Okay, finally, row 3, what that's saying is that K3 is free. Row 2 is saying negative 2 K2 is equal to a negative K3. So K2 is equal to a 1/2 K3. Row 1 is saying negative 5 K1 is equal to a negative 5 K3, which means K1 is equal to K3. So I am going to let K3 equal 2 for convenience, okay? And then K2 will equal 1/2 times 2, which is 1, and K1 will equal 2, since it's equal to K3. So our K1 eigenvector, which has components K1, K2, and K3, will equal the vector with components 2, 1, 2. And a solution associated with lambda 1 is equal to 8, and K1 is equal to the vector with components 2, 1, 2 is x1, which will equal e to the 8t times the vector 2, 1, 2. Okay, so that takes care of lambda 2 is equal to 8, but now we've got to deal with that lambda, what was it equal to? Lambda 2 is equal to negative 1 twice. Okay, so now let's say for lambda 2 is equal to -1, we're going to solve a minus a -1, so it'll be plus 1i, which is just I, set equal to 0. We're going to solve for k2 and maybe k3, so hopefully k3 as well. But that does not always happen, so we'll see which one this case is. All right, so when we plug in lambda 2 is equal to -1 into a minus lambda I, we get a matrix that has components. Let me go back to it. We have 3 minus a -1, so it's 3 plus 1, 2, 4, 0. We have a 2, negative lambda, so there'll be negative of a -1, that's just 1, and then 2, 0. And then we have 4, 2, and then 3 minus a -1, that's 3 plus 1, set equal to 0. When we rewrite this, it becomes 4, 2, 4, 0, 2, 1, 2, 0, and 4, 2, 4, 0. If I multiply row 1 by a half, and I multiply row 3 by a half, what ends up happening is we have 2, 1, 2, 0, 2, 1, 2, 0, and 2, 1, 2, 0. These are all the same equation. So if I take a negative row 1 plus row 2 equals our new row 2, and I take a negative row 1 plus row 3, that'll give us a new row 3. I can do these at the same time, and I only do that when it's very obvious, okay? So negative row 1 plus row 2, that's going to give me a row of zeros. Row 1 stays 2, 1, 2, 0, while row 2 becomes a row of zeros, and row 3 becomes a row of zeros. Okay, so what's happening here? Row 3 is saying that K3 is free. Row 2, because it's a row of zeros, it's saying K2 is also free. That's actually what we wanted. Row 1 is saying 2K1 is equal to a negative K2 minus 2K3. Okay? So what we can do is we could let K1 and K2 be any value that we want to, okay? I could choose them to be 1 and 1. That's totally fine. So we'll do that. So we're going to let K2 equal K3 equal 1. Then K1, oops, hold on. Hang on before I make that choice. I didn't fully simplify my K1. K1 is equal to a negative 1/2 K2 minus a K3. That changes how I want to define K2 and K3. I'm going to let K2 equal 2. And K3 will be 1. Then K1 will equal negative 1/2 times 2 minus a 1. So this gives me negative 1 minus 1. That's a minus 2. So our K, so here's what, oh, you know what? Hang on. Before I do that, let's not do this. I'm sorry to make this so confusing. Let's not pick values for K2 and K3, because when I do, I'm losing the fact that I get 2 eigenvectors. Let's leave them as K2 and K3. Okay, we'll choose them later. So what we got was K, and we don't know if it's like just K2 or if it's K3 or what it is. So it's just a K vector for now. And it is equal to a vector with components K1, K2, K3. K1 is negative 1/2 K2 minus K3. K2 is just K2, and K3 is just K3. Now, here's where the magic happens. I'm going to break this up into a sum of vectors, where the first vector has all the K2s, and the second vector has all the K3s. So the first vector is a negative 1/2 K2, and then the second component is a K2. The third component has no K2, so it's a 0. plus. The second vector, the k3 components are minus k3. There's no k3 in the second row, so it's a 0. And the third row is a k3. Okay. Now I'm going to factor out the k2 and the k3. When I factor out the k2, I get a vector that's a negative 1/2, 1, 0, plus a k3, and then that leaves behind a negative 1, 0, 1. Okay, what I just found is this first one. I'm just going to leave the fraction in there and everything. Okay, this is going to be my k2 vector. This second one with the negative 1, 0, 1, this is going to be my k3 vector. So I wrote it as just a k in the beginning because I was like, well, let's see what happens. Let's see if I hopefully get two eigenvectors, k2 and k3. Sorry, I wrote that as k2. And I did. I got that I've got two linearly independent eigenvectors. How do I know they're linearly independent? Well, one of them has a 0 component in the z direction. The other one has a 0 component in the y direction. They don't point in the same direction. The fact that they do not point in the same direction is why they are linearly independent. So linearly independent because k2 vector and the k3 vector point in different directions. Okay, so here's what we got. The solution associated with lambda 2 is equal to negative 1, and k2 is equal to a negative 1/2, 1, 0, and k3 is equal to a vector with negative 1, 0, 1, is x2 which is going to be, so it's a vector, it's going to be equal to e to the minus t, so that's the lambda 2 is negative 1, so we get e to the minus t times a negative 1/2, a 1, and a 0, and x3 solution is e to the minus t times the eigenvector negative 1, 0, 1. So what's interesting here is we don't get an e to the minus t. We don't put in an extra t in there because the eigenvectors themselves point us in different directions, okay? And so the general solution is x equals c1 x1 plus c2 x2 plus c3 x3. So this will equal c1, and then we had an e to the 8t, and the eigenvector that we got from it was 2, 1, 2. And then we have plus c2 e to the minus t times a negative 1/2, 1, 0. And then we have plus c3 e to the minus t times the last eigenvector, negative 1, 0, 1. And that's our final solution. We could put this together and make it look like one vector so that we could clearly see what x of t is, what y of t is, and what z of t is, okay? But we don't have to. We can write it this way. All right, so this takes care of one of the cases where we got two rows of zeros, so we had two free variables, which allowed us to come up with two linearly independent eigenvectors so that we could still form two linearly independent solutions, even though we only had one eigenvector for them, okay? So the next example does not do that. So for this system, I have x prime equals, our A matrix has components -6, 5, -5, 4 times x. When solving the determinant of A minus lambda I equals 0, it can be found that there are eigenvalues lambda 1 equals lambda 2 equals -1. Phew, they're not going to make us find the lambdas. They just want us to find the corresponding eigenvectors and the general solution to the system. So we're going to walk through how we handle this. Okay. So for lambda 1 equals lambda 2 equals -1, we're going to solve A minus lambda I, that becomes minus a negative, so plus 1I set equal to 0. And we're going to solve this for K1 and probably P. And I should say, and probably still have to solve for P. Typically, you don't know going into it whether you're going to get enough free variables in order to get two linearly independent eigenvectors. But with a 2 by 2 system, it would be impossible to get 2 rows of zeros. That just isn't going to happen. And so I already know at most I can get 1 row of zeros, which means at most I can get 1 free variable, which means at most I can get 1 eigenvector. Okay, so there is a bit of just logical thought going into that. So let's go ahead and set this up. We have in our matrix A minus 1I, we get -6 plus 1, 5, 0. -5, 4 plus 1, 0. Simplifying this, it becomes a -5, 5, 0, and a -5, 5, 0. If I take a negative of row 1 and add it to row 2, that gives me my new row 2. And we can clearly see the rows are the same. So I'm going to get a row of zeros. I get -5, 5, 0, and then 0, 0, 0. Okay, so row 2 is telling me that K2 is free. Row 1 is telling me that -5K1 is equal to -5K2, or in other words, K1 is equal to K2. So our K1 vector has components K1 and K2, and those are going to be, well, we can let them be anything we want. So we're going to let K2 equal 1, then K1 is equal to 1, so we get a 1, 1 there. And the solution is x1 equals e to the minus t times k1, which is 1, 1. Okay, so we're done with that part. We only got one solution. We should have gotten 2, and so we have to work to get that one. So we need one more eigenvector to form x2, which will be equal to, if we go back in our work, what it said was that the second solution would be formed to be the K1 t e to the lambda 1t plus p e to the lambda 1t. And so we are after p. We need one more eigenvector to form. Okay. All right, and so we were told to solve a particular equation. We need to solve A minus lambda 1I times P equals K. Okay, and so what that means is we're looking at solving A plus I set equal to K1 for P. Okay, and what that looks like is very similar to what we have above. We get a -6 plus 1 and a 5, but instead of a column of zeros, our column is formed by K1, which had ones in it. So I put a 1 on the other side of the equal bar. The second row has -5, and then 4 plus 1 and 1. Okay, so when I simplify this, I get -5, 5, 1, -5, 5, 1. Again, the rows are the same. So if I take a negative row 1 plus row 2, I get what I want. Row 1 stays the same, -5, 5, 1. Row 2 is a row of zeros. Row 2 is telling me that P2 is free. Okay, I always accidentally call this K2 because I'm so used to using K, so I'm really proud of myself for saying P2. The second one, the first row is saying -5 P1 is equal to 1 minus 5 P2. This means that P1 is equal to a -1/5 plus P2. Okay, so we can choose any values that we want for P2, right? We're allowed to pick whatever. We can be strategic or not. Your book tends to choose P2 to be like 0 or something like that because it makes it just easier. I don't always do that, but I'll go ahead and do it for now, just so you can see that we really do get to pick whatever we want. P2 is free. So let's let P2 equal 0 for simplicity. Then P1 is a -1/5. And our P vector then has components P1 and P2, which will give us components -1/5, not 1/2, -1/5, 0. And that's it. Okay, so now what we have is x2, our second solution, is equal to k1t e to the -t plus p e to the -t. So this is going to look like k1 was the vector with 1, 1 in it, times t e to the -t, plus p, which has components -1/5, 0, times e to the -t. And the general solution is then x is equal to c1 x1 plus c2 x2. So this is going to give me c1 e to the -t, k was 1, 1, plus c2 brackets, and then we're going to put x2 in there. So we have the 1, 1 vector, t e to the -t, plus the p vector, -1/5, 0, times e to the -t. And that is our final solution for this problem. Okay, looks like I gave myself more space than I needed, but I would say definitely, practice these. It gets a bit cumbersome, and there is actually a case for when an eigenvalue repeats 3 times. We'll focus on the 2 times in this class. All right. Next is the complex eigenvalues. Okay. If we have complex eigenvalues, they always come in complex conjugate pairs, which is really nice, and it actually speeds up our work at the same time that it slows it down. It speeds it up because we only have to do things once. It slows it down because we have to reduce systems of equations that have i's in them, complex number i's. Okay. So the complex conjugate pairs for lambda 1 and lambda 2 are going to be alpha plus or minus beta I. And if k1 is the eigenvector that corresponds to lambda 1 is equal to alpha plus beta I, notice it's the alpha plus the beta I, then the solutions can be formed by saying x1 equals k1 e to the lambda 1t, and x2 is equal to the complex conjugate of k1 times e to the complex conjugate of lambda 1 t. Okay, so we're going to see what that looks like. But typically, let's see if, let's say, lambda equals 7 minus 3i, then lambda conjugate is going to equal 7 plus 3i. It just gives us the complex conjugate pair. The real number 7 does not change, but the complex number 3i, that sign does change. Okay? Typically, we use Euler's formula again to rewrite our solutions in terms of real valued functions. And so here's the kind of difficult part. What we're going to have to do is calculate two things, two vectors. B1 is going to be the real parts of K1. B2 is going to be the imaginary parts of K1. Okay, what that means, let's just say that K1 vector is equal to a vector with components. I'm making this up, okay? So we'll just say 2 minus 3i, and then a negative 3 plus 4i. This could be broken up into one vector, 2, negative 3, plus I times another vector, negative 3, 4. And the 2, negative 3, that is the real part of K1. So real part of K1 is going to be that vector right there. The negative 3, 4, since it is with the I, it's the negative 3, 4 that's going to be the imaginary part of K1. We don't bring the I with it. We just take the vector that was associated with I. Okay? Let's see. So when dealing with complex eigenvalues, this is a big note, we just simply work with the one that's of the form lambda 1 equals alpha plus beta I. We'll be able to get both eigenvectors for free on there. The second note is that if you have complex eigenvalues, the solution will be a complex valued solution unless you get it into the trigonometric form that we have above. We want real valued solutions in this class, so you must get your solutions into this form. So that form says that the x1 vector solution is going to have an e to the alpha t on the outside, but inside the brackets we have b1, where b1 is the real part of k1, times cosine of beta t, minus b2, where b2 is the imaginary part of k1, times sine of beta t. In the x2 solution, things switch a little bit. We get the e to the alpha t outside the brackets still, but inside we have b2, the real part of k1, times cosine of beta t, plus b1, the real part of k1, times sine of beta t. I think I said that wrong. I said that b2 was the real part. It's the imaginary part of k1. Okay, let's do an example so we can tie this all together and then be done, not only with this section, but with this chapter and with this course. So let's find the general solution of the given system. X prime equals the matrix with components 4, 5, negative 2, 6 times x. We first need to find the determinant of a minus lambda I and set it equal to 0 and then solve to find lambda. So that means we're looking at vertical bars. Inside we have 4 minus lambda, we have a 5, we have minus 2, and we have 6 minus lambda. We do our diagonal product, and we get that this is equal to 4 minus lambda times 6 minus lambda minus a negative 10. So it'll be plus 10. We set this equal to 0. I need to FOIL distribute combine like terms. So this becomes lambda squared minus 4 lambda minus 6 lambdas minus 10 lambda plus 24 plus 10 is equal to 0. So this is saying lambda squared minus 10 lambda plus 34 is equal to 0. There are no factors of 34 that add to negative 10, so this does not factor. We need the quadratic formula. Lambda is equal to negative b, so it'll be a negative of a negative 10. That's a positive 10 plus or minus the square root. B squared is 100 minus 4 times 1 times 34, all divided by 2 times 1. This gives me 10 plus or minus the square root of 100 minus 136, all over 2. And this gives me 10 over 2 plus or minus. Looks like I get a negative 36 under the square root. And the square root of negative 36 is a 6i. And then that's over 2. So this simplifies to be 5 plus 3i. Alpha is 5 and beta is 3. And I've lost my minus. There we go. Make my beta a little bit nicer to look at. Okay. Now, for lambda 1 equals alpha plus beta I, so we're going to look at 5 plus 3i. We need to solve a minus, in parentheses, 5 plus 3i times the identity matrix set equal to 0. Let's see how to handle this. All right, so I plug this into my a minus lambda I, and I get 4 minus, in parentheses, 5 plus 3i, a 5, and a 0. Second row, I get a negative 2, and I get a 6 minus, in parentheses, 5 plus 3i, and then a 0. Put my equal bar in. Now I simplify this. So then it becomes a negative 1 minus 3i, a 5, and a 0. I have a negative 2, and I get a 1 minus 3i, and a 0. Okay, now what I decided to do in this one is to multiply row 1 by the complex conjugate of negative 1 minus 3i. The complex conjugate of negative 1 minus 3i is negative 1 plus 3i. And you'll see why I did this in just a moment. Basically, I want my first column to have real numbers so I can work with them a little bit more easily. Okay? But I need to do some of the algebra for this on the side. Okay? So number 1 is that negative 1 plus 3i times negative 1 minus 3i. I got to figure out what that multiplies out to be. So it gives me a positive 1 plus 3i minus 3i minus 9i squared. The minus 3i plus 3i go away, and I get 1 minus 9i squared is actually equal to negative 1. So this becomes 1 plus 9, which is equal to 10. Okay, so our new matrix, what it becomes is the first component in the first row is 10. 5 times the negative 1 plus 3i just gives us, let's see, how do I want to do it? I'll go ahead and distribute it. No, I'll leave the 5 out. Okay, times the negative 1 plus 3i, and then a 0. And then I have a negative 2 and a 1 minus 3i and a 0. Okay, now if only the first row in the first column was a positive 2. Well, if I was to multiply row 1 by a 1/5 right now, it would be a 2. And so I'm going to do that, 1/5 row 1. Basically, I'm doing a lot of work to get row 1 in a good position to use it to clear row 2. So if I divide the whole row by 5, I get 2. I get a negative 1 plus 3i. I get 0. And I get negative 2, 1 minus 3i, and 0. Now, if I just add row 1 and row 2, that's going to clear row 2. So first row is 2, negative 1 plus 3i, and 0. But the second row is now a row of zeros. So K2 is free. That's what row 2 is telling me. Row 1 is saying that 2K1 is equal to, if we move that over, it becomes a 1 minus 3i times k2, which means that k1 is equal to a 1 minus 3i over 2 times k2. So I need to let k2 be a convenient number. I'm going to let k2 be 2. So then k1 is equal to 1 minus 3i. And our eigenvector k1 is equal to the vector with components k1 and k2. We plug those in. k1 is 1 minus 3i. k2 is 2. We rewrite this so that we can see a sum of a vector plus I times a vector. So I have a 1 and a 2, and then plus I times the vector with a negative 3 and a 0. So I've broken it up, and then I can say that B1, the B1 vector, that's going to be the real part of K1 vector, that is equal to the vector with components 1, 2. The B2 vector is equal to the imaginary parts of the K1 vector, and that is going to be the vector that has components negative 3, 0. Okay? And now that we've identified those two pieces, we can form our solution. Okay? So just to recall, I'm going to go back up real quick. X1, we have the e to the alpha t on the outside, and then we have b1 cosine of beta t minus b2 sine of beta t. X2, again, we have the e to the alpha t on the outside, and then we have b2 cosine of beta t plus b1 sine of beta t. Okay, I give those on a formula sheet. I'm not expecting you to memorize those, but you do need to know how to find b1 and b2. Okay, so we go back down, and we can say that x1 is equal to e to the alpha. Alpha was 5, so e to the 5t, and then in brackets we have b1. b1 has components 1, 2 times cosine of 3t, and then we have minus b2, which has components negative 3, 0, and then sine of 3t. I put 3 because beta was 3. I should have been more clear about that. Alpha's 5, beta is 3. That's coming from our eigenvalue. Okay. X2 solution is going to be e to the 5t, that's our alpha, times, now we have b2 that comes first, so it's negative 3, 0, times cosine of 3t, and then we have plus b1, which is 1, 2, times sine of 3t. And the general solution, I won't write it out, but I'll just point out that the general solution is x equals c1x1 plus c2x2. Okay? And that is all I have. We are done with the eigenvalue problem. We are done with differential equations. But as always, please feel free to reach out for help.